Okay, so in your notes, we are going to review more of what we talked about at the end of last week, but we're going to continue looking at kind of how the numbers are affecting our graphs. Zoom here. So we are still just kind of continuing what we started. Okay. All right. So we're still looking at exponential functions. So graphing. We can call it 2. So graphing exponential functions 2. Yes. Is what? No. There's a new page. There's a new page. All right. So again, our goal is to continue trying to figure out how these different numbers are affecting the way our graphs look. Because if we can understand how the numbers change, then it makes us more efficient when we're actually graphing. So what we're going to do is we're going to create a table for 2 different functions, kind of like we did last week, where we had different things happening and kind of see what the number does. But we're going to look at some other things that will happen. So example 1, our first function is going to be 1/2 to the power of x. We're going to make a table. Now, one of the things about the tables is that at this point, if you are going through the calculations, you're doing too much work. Okay, we want to start becoming more efficient. So we're going to identify the A and the B so that we can complete our table faster. All right. Now, until you get comfortable, it's different if you want to check yourself. But at this point, we want to start using our brains to work smarter, not harder. Right. So I have an A and I have a B. Right. Remembering that my general function is A times B to the x power. Right. So in my first function here, what's the A? 1. The B is the base of my exponent. It's 1/2. Now, remembering that the A is our first term, and in this case, when we're graphing our functions, the first term is actually the y-intercept. Okay, and we saw that last week as well. So the A is actually going to be our y-intercept. It's our first term graphing-wise, and then the B is our ratio, right? So when we create our table, and let's do -1, 0, 1, 2. So when we make our table, since my A is 1, and I know that's my first term or my y-intercept, that matches up with x equals 0, right? So this is our y-intercept, and this is our ratio, right? So that means that everything is going to be multiplied by 1/2 to get my next point. So my next point here is 1/2, because remember, this is a geometric sequence, right?
Would -1 be -1?
Nope. So if we want to work backwards, I would need to, if moving forward I'm multiplying by 1/2, moving backward would be like dividing by 1/2 or double, right? Dividing by 1/2, if we think about we don't divide fractions, we make it multiplication and find the reciprocal, right? So dividing by 1/2 is like multiplying by 2. Right? So if I cut something in half one direction, doubling it goes the other direction. It's like the opposite of cutting something in half is doubling it. Right? So if I want to move backwards, another way you can think about this is what number would have to go here so that when I multiply it by a half, I get 1. 2 times a half is 1, right? The other option, like with a calculator, if we know our ratio is 1/2, you take 1 divided by a half. Okay. You'll just have to come up with the strategy or the method that makes most sense for working backwards. So if moving forward is multiplying, the opposite would be dividing, right? So if I have to multiply each of these by 1/2 to move forward, I divide by a half to move backward. Yeah, so my number's gonna get bigger moving backwards, right? Okay. All right, so take a second and actually, no, we'll wait for the Desmos part. Okay, we're gonna do a second function real quick. It's not number 2, it's actually we're gonna compare. So our second one is f of x equals 4 times 1/2 x. And we're gonna make a table. We're gonna identify our a and our b. In this case, the a is 4. B is still 1/2, right? So when I pick my numbers, I want to include a 0. The a is our y-intercept. So I know that when x is 0, y is 4. If for some reason you don't remember that, or maybe we haven't practiced enough or you haven't practiced enough, whether you did all the practice but it just wasn't quite enough for this to kind of commit to memory, a backup for something like this, with tables, having your x as 0 is usually one of the most efficient numbers to substitute, because 0 starts kind of knocking out a bunch of work, right? So what you can always do is look at this and try to find your y coordinate for the 0 first, because it should be the easiest one to find, right? If x is 0, then this whole power becomes 1. 4 times 1 is 4. And then follow the geometric sequence. So you can find that value first and then know that it's a geometric sequence. So from there, I can start following with my ratio, right? So this would be 2 and then 1. Yes?
I thought B was I remember, but when it was like putting it, I thought B was the y.
B is our ratio, because if you think about it, it has the exponent.
Right.
And so if I want the 4th term, I had to multiply the number by the ratio by itself over and over and over and over.
Okay.
And anything with an exponent is repeated multiplication. So this number here tells me what keeps getting multiplied over and over in my sequence, which is the ratio, right? And then if I back it up, I get 8.
I remember y equals mx plus b.
That's for linear, that's for straight lines. That b's still the y-intercept, but it's not the same b that's here.
Okay.
Yeah, they repeated an alphabet letter. All right. Okay, you're welcome. So if we look at our 2 tables for a second, if you compare our y values, do you see how each step of the way, my y value in this second function is the other y multiplied by 4? Can you guys see that? Which makes sense, because when we take our power, we multiplied it by 4 over here. Okay, so what we want to look at in just a minute when we graph these is how did having that a become a 4 change the graph? And we could probably say that, well, it obviously is going to change the y-intercept, right? But we're going to see how else it changes our graphs. So on your Chromebook, take a second and go back to Desmos. So go back to Desmos, and we're going to clear out the function that we had originally in, and we're going to actually put both of these in. They're going to each get their own line. Okay, so let me zoom over here. Make sure that when you put the half in, it's in the parentheses. If you don't, you are not going to get the same line that we're supposed to get here.
How do you do that? How do you go?
When you're typing it in? Yeah, so when you're doing your parentheses, you do the first parenthesis, and as you type, if you try to type a second parenthesis, it's gonna force it down at the bottom. So I backed it up. If you either click outside of that gray one and then continue, it'll make the gray parenthesis an actual
How do you
parenthesis.
do the X?
Shift 6.
Why? Okay.
And when we have a fraction as our base, it does make it a little bit harder to see that you actually have the exponent as the x, that you did that right. But we know that you did it right if your graph looks how we're expecting it to look, right? If I didn't have that as an exponent, I would end up with either nothing or a straight line. Something weird would happen, right? Okay. All right, so if we take a look at our two graphs, let me scoot over here a little bit. Then zoom out. If you're really close, you might not notice the difference. And on the packets that we did last week, it was harder to tell how similar our curves were. So make sure you zoom out a little bit so that you can see exactly what's happening. So our red one is the 1/2, which we could consider like the parent function. Okay. It's a parent function when the ratio is 1/2. And my blue one is when our A becomes a 4. So if we look, our y-intercept definitely changed, which we knew, right? We knew that our first function would have a y-intercept of 1, and our second function would have a y-intercept of 4. And on Friday, when we went through this, all we really saw was like this part of the graph, and it actually kind of looked like it had been stretched, or like it wasn't really the same exact curve, just in a different position. But if we look at it now, can you kind of see how it's actually the same curve, just shifted over, at least at this part of it, right? Down towards the bottom, it changes a little bit. But for the most part, it's like the same curve, just shifted, all right? So the A changing on Thursday and Friday, or I think it was Friday, all we really said was that it changed the y-intercept, but actually it shifts the whole graph, all right? So if it's a positive 4, our graph shifted to the right. Do you think if my A was a negative 4, do you think it would shift to the left maybe? Okay, and that's the nice thing about something like this is we could actually just take a second, we wouldn't have to even make a new table. You could make that negative, and it actually didn't. It actually created a mirror image of when it was positive. So it changed the y-intercept, but it kept its like position relative to the x-axis. So those are the kind of things that we want to start like kind of finding patterns with. All right. The other thing that I want to look at, and we're going to talk more about it, I think Wednesday. If you notice, as you kind of drag to the right, do you see how it's kind of hard to tell, maybe easier on yours? It looks like both my curves just end up having a horizontal line, right? And it never really crosses over. Okay, when we talked about the vocab, there was a vocabulary word, asymptote. And the asymptote is a line that's kind of like a barrier, and our curve will approach that line and just never ever cross it. That's what this is showing. This is showing that the x-axis is actually our asymptote. So this imaginary line here is actually keeping our curves from crossing over. And then I think on Wednesday, we'll see what part of the graph or what part of the function makes that happen. All right, but if we were to kind of scroll up higher, our graphs here do keep moving in like to the left, right, as we go. All right, and I click home and it gets me back here. All right, okay. Next thing that we're gonna do is, we'll do this part next. Okay, example 2. So go back to your notes for a second. You don't need to close the Chromebook because we're gonna come back to it in just a minute. All right, so we're going to do a second example, kind of similar to what we just did. And my first function is going to be -1 times 1/3 to the x power. And we did see last week how having our a negative, what happens, and we just saw it on Desmos, that when we made the a negative, our graph of the curve kind of mirror image down, like it reflected over the x, right? So let's quick do a table for this. Identify our a and our b. And I know it's gonna feel like at one point you don't really need to do that, but it takes 2 seconds and it keeps you organized, right? So then on a quiz, which I think Wednesday, there's gonna be a short quiz on this. So my a is -1, which is my y-intercept. My ratio is 1/3. So I'll just be multiplying by 1/3, right? That's -1/3, by the way. -1/9. This might be an area you might need to calculate. The one thing I would suggest is that repeating decimals, like 1/3, you don't want to try to avoid writing as repeating, especially if you can make it a fraction. 1/3 should be one that should be kind of ingrained in your head as the fraction for the repeating decimal. Did you find it? I'm sorry, dude. What were you looking for? A what? Okay, did anybody find a pencil back there and keep it? No? Okay. All right, so let's look at a second function. Okay, so we have f of x equals -2 times 1/3 to the x. What happened? You're not in the 6th grade? So sweet. I know. Who knows? He probably has a teacher that like takes a shoe and he does not want to take his shoe off. I would have given him a pencil. He just ran out too fast. You guys are very intimidating, apparently. You're very scary, 8th graders. All right. So let's do our table here. And just like up above, when my a was a 1 and then it became a 4, all of my y coordinates had been multiplied by 4, right? So if we look at the pattern on our tables, up above, like I said, when my a changed to a 4, all my y coordinates actually were multiplied by 4, right? 2 times 4 is 8, 1 times 4, 1/2 times 4, 1/4 times 4, right? So I multiplied my a by 4 to get this a, so all my y coordinates got multiplied by 4. So if we look at this, something like that could possibly follow as well. And these are all kind of strategies to help you be a little more efficient. So since my a was multiplied by 2 or doubled, my x values should probably double on this table. Now that might be a little more like trusting of the process than maybe you want, but ultimately, if I look here, my A is -2, so my y-intercept is -2. And if I look at the other y-intercept, or excuse me, the other y value, -1 times 2 is -2. So it should follow that I would have -2/3, which is correct because if my ratio is 1/3, -2 times 1/3 is -2/3, right? Which would also give me -2/9. So -2/3 times 1/3. 2/9. Nope. And then if I back up, I would get -6. -6 times 1/3 is 2, so I know I'm correct. You can always go back and check, double check your math. But our goal is to start becoming more efficient with what we can be more efficient with. All right. And then in Desmos, let's graph both of these and see what happens. You shouldn't need to, like, you don't have to delete everything out. You should be able to just kind of adjust what you have in Desmos. And that's something too, as you adjust your functions here, you can kind of pay attention to see the changes that happen. You can kind of zoom and recenter here. And again, it looks like the same curve, just shifted, which is similar to what happened on the others. It's just that our A is now negative, which means our curve is going to be on the bottom half of our graph. Right. Good. All right. So again, the ratio, excuse me, the A, our first term A there, does shift the graph, right? Other things that we can look at is we can also compare the B's, and I know we did that on our packet, but for some reason when you're using like one of these online calculators, graphing calculators, it makes it a little bit easier to kind of see how things change. So we could even adjust and say, okay, well, how does it change if it was 1/3 compared to 1/2? And we can see how our lines adjust. So as you guys are, doing your assignment tonight, you will be able to use Desmos so you can check yourself. Pay attention to how things are changing because the more you can find the patterns in that, the better. All right, so for the assignment, we actually did numbers 1 and 2 with some extra stuff. So we're gonna graph them together really quick just to make sure you have everything done that you need. This paper does not have tables or room for tables. Well, you might be able to squeeze the tables in there. If you don't want to squeeze the tables on this paper, you can continue. You can continue in your notebook. So again, if you don't,
It's so funny.
if, like I said,
You're wearing stickers.
if you, if you don't want to kind of squeeze the tables on this page, you can do the tables in your notebook. But for the graphs, if you notice on your paper, there is no coordinate plane. It's just a grid. So, oops. Uh-oh. So what you're gonna have to do, and what you'll notice too, is we did like a second function. You don't have to do both like I did here. Okay, this was just so that we could compare what happens when the A changes. So all you would have to do, like for number 1, would be this table because that matches the function, right? And so then when you go to graph it, you want to just kind of pay attention and look and see like what quadrant or what area of the coordinate plane you want to make sure you have available. So, for example, I need to have at least one negative value on my x's. My y's I can keep all positive. So I would have like the first quadrant on my graph for this one. That makes sense. So when you draw your coordinate plane, just make sure that you have enough space to get everything graphed for the one function. You do not need to label your intervals unless they are not going by ones. So if your intervals on your grid are by ones, you don't need to label like the numbers. Okay, now the directions do say identify the domain and range and the asymptote, but we're not going to do that yet. So you can actually ignore that part. It says create a table or label your points on the graph with the ordered pairs. You're going to do both. It doesn't take much longer. So definitely make a table. You can do it in your notes, or you can find room on this page. Definitely plot the points and label the points. So for our first one, 4 times 1/2 x, just make sure you label your ordered pairs and then graph your curve. And that's it. And you could definitely keep Desmos open and use that to double check that everything looks right. But this is your assignment. That's it.